Hi everyone, my name is Gokul. I'm the Director of Technology for Robots.Expert. In the coming few slides, we will talk more about who Robots.Expert is and what we do. Robots.Expert is a part of the 5G drones consortium, which is a Horizon 2020 EU project funded by the European Commission with partners from all across Europe. And in this presentation, we will talk about a few use cases that the 5G drones project is focusing on, and specifically related to urban air mobility and 5G technology. Besides that, Robots.Expert also was a part of the Gulf of Finland U-Space project. This was a huge demonstration project that happened in 2019, and the results of this project was phenomenal. One of the first results of this project was the first unmanned flight between Estonia and Finland. And this flight was unmanned and fully autonomous, and this was the first flight to be performed between Estonia and Finland under the U-Space regulations. The aircraft was owned by 3 Systems, and this picture is under the copyright of their company. And the second result of the Gulf of Finland project was the first ever air taxi flight inside an airport. So the Volocopter air taxi took the first ever flight in Helsinki-Vantaa airport. And Robots.Expert was privileged to be a part of this project, and we facilitated these trials and helped the companies with flight permissions and licenses and certifications. Outside of these 2 European projects, Robots.Expert is also actively involved with NASA in the Advanced Air Mobility project, and we are part of the technical working groups, advising them on issues related to crashworthiness, airworthiness, noise, and such topics. And then we're also actively involved with the African Drone Forum, where we are actually advising the unmanned aerial vehicles group for payload delivery. So these are long distance drone delivery missions, and we are really privileged to be a part of these 2 forums. Coming to the topic, urban air mobility, the first use case we will discuss is BV loss operations, which is beyond visual line of sight. Beyond visual line of sight could mean that the drone could fly anywhere outside of the visual line of sight, which means that you don't have a visual perception of the drone anymore. You have to rely completely on the instruments and the data coming from the drone. As we can imagine, beyond visual line of sight is not fully accepted yet. There is a lot of regulations in place. The companies doing the beyond visual line of sight would have to go through certifications and permissions from EASA and FAA and those kind of regulatory authorities. So the first thing that's needed is we have to reassure safety, which means we have to go through SORA, which stands for Specific Operational Risk Assessment, and JARUS. These 2 are heavily used by EASA to evaluate how safe the drone operation is. And we need connectivity to perform BV loss missions. Connectivity enhances the situational awareness, and connectivity in a way also guarantees that the drone is going to be safe. So if we have connection with the drone and the connection is stable, we can control the drone in some way or the other. Now, speaking of connectivity and connection to the drone, the next immediate topic that I want to discuss is data transmission. There cannot be any delay in data transmission or latency. So hence, we rely on ultra reliable low latency communication. And finally, unmanned traffic management, which is UTM, and command and control centers, which is the ground control station. This is critical in order to be able to track the drone or the aircraft and ensure the safety of the airspace. You don't want a situation where your drone is performing a BV loss mission and you lost connectivity, and the traffic management is not able to see or track the aircraft anymore, and you have no control over the aircraft anymore. That's quite a dangerous situation. And all of that goes back to SORA and JARUS and those safety measures. So what are we doing to ensure connectivity? What are we doing to make sure that there is no delay in data transmission? Now, if we think about all of these things, in a way, performing BBLOS missions and taking all of these into consideration is almost the same as juggling while riding a unicycle while you're completely blindfolded. And it's not very different, right? So that's where the 5G technology comes into picture. With 5G, you're able to have guaranteed connectivity, and you can have dedicated slices for missions. So every time you perform a BBLOS mission, you can actually dedicate a slice from the network to make sure that this drone has connectivity throughout the mission. And then comes low latency data transmission. And this is really critical, because if you have an aircraft flying at 20 meters per second, and if you have 0.3 seconds or 300 milliseconds latency, that drone could have actually traveled quite some distance before you actually know it traveled that much distance. So minimizing the latency as much as possible is really critical. And finally, all of these things will lead to enhanced real-time or near real-time tracking for UTM and command and control purposes. In the 5G drones project, they are looking at this use case for BBLOS operations, and we have several verticals that we are trying to do, and all of them come under the BBLOS category. And in this case, we have the drones that are connected to the 5G network, and the drones, all of them have the INVOLI tracking system, which is almost similar to ADSB or a GPS, if we can say. And that data is reported to the UTM system, and the UTM system is in a way connected to the 5G trial engine, which is also connected to the command and control or the ground control station, which is controlled by the pilot, right? And the pilot has a direct C2 link or command and control link to the aircraft, and the aircraft can send and receive messages through the link. And then we also have a video telepresence, or FPV, if I can say that, first person view, live feed of the video from the drone to the pilot's computer. And also the telemetry. With all of these data coming in, we can ensure that the operation is fairly safe. The next topic I would like to discuss is multipath error. Before we go into multipath error, I want to give a broad outlook or a high-level architecture of what a flight controller is made of. This is kind of what a flight controller would look like. You have multiple pieces connected together. It's an embedded system. And the highlighted area here is on board the drone. It's not something that the user can directly interact with. They have to be connected with the drone, right? And the navigator is a system that has the waypoint information in terms of GPS coordinates and map information related to flight path and vectors and everything. And the RC is the one that receives or that provides the human input, and it goes directly to the position controller, and the position controller can receive inputs from the human being saying roll left or pitch forward or something like that. And that information is sent to the attitude and weight controller, and so on, so on. Now, the key part here is the sensors. The sensors can be a GPS on board the drone. It can be a video camera. It can be your LiDAR for situational awareness, anything. In this case, we want to consider the GPS receivers, which provides values to the position and attitude estimator, which has algorithms like extended Kalman filter and several other sensor fusion methods, which combines the IMU of the aircraft with the data from the sensors and tries to understand where it is currently. Now that's where we go into multipath error. When you have signals from satellites, reflected off of building structures like glass windows or design and decorations on buildings, and the reflected beams fall on the sensor or the GPS receiver, it can directly impact the triangulation that's being done as a part of the position estimator. What that means is that if this multipath error continues to happen, the sensor would not know the true position of where the signal is coming from and where the drone is actually currently located. Now, what this would look like is if we were to take the city of Brussels, which has a lot of tall buildings with glass structures and windows and other things, and also in the bottom right corner of the screen, you can see this pyramid-shaped glass structure, which is a source for multipath error. In this case, what would happen is the drone would think that it's in this location, and the calculations would show that the drone is in another location, as shown in the picture. And this is what the user would see on the map. But ultimately, the drone is somewhere else. This is a real problem in terms of situational awareness and controlling the aircraft. If you are doing a visual line of sight flight, this is not a huge problem because you can directly see the drone and take control of it and make sure that you don't fly into buildings or you don't fly into cars or anything. But when you're performing beyond visual line of sight operations, this is extremely dangerous. And this is more prominent in urban settings. And the multipath error does not come only from buildings, glass structures, or windows or such things. It also comes from reflection from the top of vehicles. So if you have a lot of vehicles on the street, you could have satellite signals bouncing off of those vehicles and going to the drone, which is maybe flying at 15 meters. And that would affect the position, navigation, and timing of the vehicle or the aircraft. And this affects both the horizontal and vertical accuracy in terms of calculating where the aircraft is currently and where it's heading to. And of course, impact of all of these things is that the situational awareness is kind of grayed out. You really don't know what's happening with the aircraft, and you're not sure what to do next. Ultimately, this would deem the operation unsafe and infeasible. Now, with 5G, we can have edge computing and cloud computing. So you can have mech devices on board the aircraft, which would enhance the situational awareness by providing near real-time computing, so that you can have a camera on board and you can have not GPS sensors, but mobile trackers like the one from Involi we saw in the previous use case, which would directly connect with the UTM systems or even the user's map and give you an accurate estimate of where the vehicle is currently located or where the aircraft is currently located. And it enables more optimized and accurate tracking of the aircraft. Like I mentioned, position, navigation, and timing, in short PNT, and reliable C2 link, which is command and control link, is critical. And we see that 5G technology is going to enhance these capabilities by providing dedicated slices and guaranteed ultra reliable low latency links to ensure that you can do edge computing and cloud computing in near real time, and then make sure that you know where the aircraft is and you know what's happening around the aircraft. There are a few other use cases related to UAM and 5G drone project using the 5G technology. Due to time constraints, I'm not going to go into details of these use cases. I'm just going to quickly go over them. We are considering use cases for first responders, where firefighters can use drones deployed on the 5G network to enhance situational awareness. For example, there's a building that's on fire, and the firefighters would have to use drones, and they would have to send the drones inside the building. So you could have a private 5G network that's dedicated for the fire department in that location, so that they don't have to share the bandwidth with other users, and they can have near real-time data transmission to accurately show them what the situation is. Another use case is the police and law enforcement officials can use drones and 5G technology for surveillance and crowd monitoring. This is something that's becoming more and more common, but the use of 5G will definitely leverage the capabilities. As we've seen in the last few months, drones have been used in pandemic situations like COVID-19. And also, we are evaluating the use cases where drones could be used in heavily crowded environments like stadiums and malls and fairs to enable more enhanced data transmission that can be shared by many people, like a crowd. Now, all of this is amazing, but we need to talk about the bad side in terms of challenges. Why are we not there yet? Why are we still in trial phases? Why are we still experimenting with things? The first reason that I would say is lack of business models. There is still a lot of investigation that needs to be done in terms of how these business models are going to work out. How are people going to use 5G and pay for it in terms of monthly subscription, or are you going to pay per gigabyte of usage? These are some topics we are currently experimenting in our 5G drones project, and that's one of the deliverables that we have committed to the European Commission, that by the end of the project, we will be able to provide with viable business models that will work out for the telecom operator, drone operators, end users, and pretty much everyone in the ecosystem. The next problem is scalable deployment in terms of use cases. This also touches a little bit on the beamforming and those kind of properties of the base stations and nodes and cells. How scalable are these deployments? How wide is 5G coverage going to be? How many base stations to deploy? All of these things will be driven by demand, and these are still early days, and telecom operators are still evaluating the demand in the market and trying to understand how this is going to work out. Next comes the classic topic of millimeter wave versus range versus low band spectrum. To perform BVLOS mission, you want enhanced coverage. You want really long distance coverage, like 30 kilometers, 40 kilometers. For that, you would ideally need a low band spectrum, which has a wider coverage. But the problem with wider coverage is that it does not guarantee low latency, which requires millimeter wave if you want to have low latency. So there's going to be a trade-off between low latency capabilities and extended range. And this trade-off has to happen at telecom operator level and drone operator level in deciding what kind of missions can be performed over 5G and what kind of missions are more realistic. So like I mentioned, it's still early days, and hopefully by the end of the 5G drones project, we will be able to provide more clarity on these points with evidence from experiments and sufficient statistical data to show that things work the way we expect it to work. And as for every technology, we have to go through Gartner hype cycle. And as of August 2019, 5G technology was in the peak of the inflated expectations, which means that the next few years is going to go through a decline and a trough of disillusionment before it starts going up the slope again. And this picture is from IEEE website. I'll be happy to provide references later. But this basically tells us that the use of 5G technology is not going to be adopted by regular day-to-day customers in the near future. It's going to take a few more years for the adoption to happen, and slowly it will be used alongside 4G and just like how we have 3G and 4G working together today, we are going to have 4G and 5G working together. So that's one topic. And finally, public acceptance. This is a huge topic for both urban air mobility and 5G technology. How comfortable are people when they see drones flying in and out of city centers? How comfortable are they with 5G technology? For instance, there has been a few incidents related to the public destroying 5G towers and such things. So public acceptance is still a widely explored topic, and we might have to do a little more investigation into how this can be implemented. So with all of that, I would like to thank you on behalf of Robots.Expert. And I would like to thank for this opportunity to present who we are and what we do and what we're doing in the 5G technology project. If you have any questions, I'll be happy to answer them at this point. Thank you so much.